Hey, this is Chad Houston. We're going to do a flipped assignment here on acid-base chemistry. Now, acid-base chemistry, there is just a ton of stuff to talk about. It's really, really important because in the world, when you look at the top 10 chemicals produced every year, the top five are all either acids or bases. So there's just all kinds of stuff going on with acid-base chemistry. So the first thing I'd like to do is just to talk to you a little bit about just what are acid and bases. Okay, so first of all, let's talk about the symbolic part first. There's a couple ways we can define acids and bases. Probably the easiest is this. Okay, so we'll look at a couple of these. An Arrhenius acid has any species that produces hydrogen ion plus one ion in water. An Arrhenius base is any species that produces OH negative. So if you see an H plus, think acid. See OH negative, think base. Another way to think of it is that a Bronsted-Lowry acid is, if you look down here, is anything that that donates a hydrogen ion. So just a slightly different way to think about it. The Bronsted acid, okay, so means this definition says it's a proton donor, and a Bronsted base down here basically sees this as a proton acceptor. Why the distinction? Because basically a Bronsted acid and a Bronsted base can be an Arrhenius acid and base, but also the other cool thing about it is there are many other things besides OH negative that can actually accept a proton, which is the H plus. That's basically a proton. The other part too, if you go on to other chemistry courses, you'll talk about Lewis acids and bases, and a Lewis base has an electron, donates an electron pair. So imagine this electron pair here, that would make this a Lewis base. And then the Lewis acid accepts an electron pair. So one way to see it. So it basically is able to involve many more chemicals that essentially do the same thing. Okay, so that's a definition of what they are. And also we're going to jump out here for a second and cruise to one of my favorite sites on the planet is Adam Smith, because this really shows you a cool model. This right here is acetic acid plus water. And here, if you look over here, the acetic acid, there's the acidic proton. We're going to get rid of that proton. And then the water here is going to accept the proton. Think Bronsted-Lowry acid base. So here's a water. You can see this right here. There's a water. Here's the acidic proton. Even though there are other protons here, this is the one that's going to give up. And as we do this, one gives up and one goes to it, and that's an acid-base reaction. So here's the acid. Here's the base. Water's acting as a base, which is kind of cool. It can also act as an acid. And the other part, which is kind of neat, is this is now, if we go back the other way, which is possible, this will accept the proton. This will give up a proton. Now, going the other way, water acts as an acid, and this anion acetate acts as a base. It's called the conjugate base, conjugate acid pair. Kind of neat. So just some cool stuff there. So let's go back to this one. We'll take a look at some quick little properties here. Down here, acids love to eat through metals. Big problem that occurs with that is acid rain can really do some damage on cars. The metal ions can get into all kinds of nasty underwater stuff. A couple of things here. Properties of acids. They taste sour. Think of like juices or acids. They always give off H plus ions. They change the color of indicators. There's lots of indicators out there. Most of them come from plants. It turns blue litmus red. Think acid and red match or rhyme a little bit. They have a pH, and we'll go into pH a little bit later, much later, between 1 and 6.9. Stings if you get it on your hands or on your skin. And of course, we said it reacts with metals. Now, properties of bases. They taste bitter. I know that Dutch chocolate is somewhat basic. It has a bitter taste to it. They're never stored in glass because they react with glass. They also tend to feel, they produce OH negative ions usually. That is the definite sign of a base. They change indicators red litmus to blue. pH high or pH from 7 to 14 feels slippery on the skin. It's in soaps, and the reason it feels slippery, it's actually peeling off a scale layer of skin, and that mixes with water, and it feels like an oil type thing. These hydrangea bushes are in my front yard because if you mix a little coffee grounds in the soil, you slightly change the acidity in the soil, and you can change the color of the plant because it essentially is an acid-base indicator. These are common acid and bases you can find: lemon juice, vitamin C. This is vinegar over here. These are all bases. Baking soda, Drano is really strong base. Got to be very, very careful. Now, a couple other things. I really like this over here, this pH scale. We'll go into pH later. The biggest thing I'd like you to know about pH is this. This scale, below is acidic, high is basic, 7 is neutral. Below 3 and above 11 is dangerous for our skin. This goes by a factor of 10 in concentration, which means if you have something at a pH of 6 and then it goes to pH of 3, it's not twice as acidic because you change a factor of 10 each time. That's okay. So we start at 6. That's 5 would be pH of 5 is 10 times acidic. pH of 4 is 100 times acidic than 6. pH of 3, 1,000 more times acidic than a pH of 6. So we'll go into pH more later on, but just realize there's a big, that it's not a linear scale. It's a logarithmic scale, okay, on the base 10. And that we're going to have to talk about later on. Now, the other thing you're going to have to brush off and know is whenever we're dealing with acids and bases, the concentration has to be done in molarity. Molarity, again, is the number of moles per liter of solution. That's the quantitative way of dealing with acids and bases. And when we're dealing with this molarity, we can pour out the exact number of moles that we need. So if I have 1 molar HCl, if I have a liter of it, in that liter is 1 mole of hydrochloric acid. Excuse my dog barking. Then, if I pour out a half a liter, I get half a mole. If I pour out a quarter of a liter, I can get a quarter of a mole, a tenth of a liter, a tenth of a mole. It's a great way to deliver the exact amounts that we need. Now, next thing is, let's see, pH. We'll talk more about the pH scale later with pH. This right here is a cartoon that I found, and I'm just going to, you can just look at this. But whoever did this knows their chemistry and is a pretty gosh darn good artist, I'd say. I just thought this was kind of cool because I'm just not that creative, but it's good science. It really is. This really is a good cartoon that talks about the differences. And this is not a student that I had. I got this from somebody. I don't know who it was. But yeah, this is really nice. Acids are sour, pH over 7, vinegar. Oh, also because there's ions, they all conduct electricity. Usually, and I didn't talk about this, strong acids go 0 to -4 pH. Weaker acids are 3 to 6. Again, strong bases 10 to 14. Weaker bases 8 to 10. A lot of soaps and detergents here. Again, these can accept protons. These give up protons. Proton donors. We talked about lemon, acid rain, antacid tablets, things like that. So anyway, this is kind of a great little thing on just the properties of acids and bases. So, okay, so that I believe pretty much wraps up acids and bases. The next flipped assignment we're going to do, again, this is just some essential properties. And again, the other thing which I forgot to mention too, because of these ions, they conduct another. Oh, that's saying I need to quit talking pretty soon. And finally, most of the time, acids and bases react usually to form salt water and to go neutral. That's also a pretty important thing. So there you go. And thank you for listening. And I certainly hope that this was helpful.